talking about forces. Now, what do we know a force is? Mathematically, you probably learned in physics that force is some mass times acceleration. But before we get to that point of making that calculation, we have to look at it in terms of the force being a vector quantity. Now, what does a vector quantity have that makes it different from any other type of quantity?
Direction.
Okay, it has direction. And it has magnitude. Okay, it's got to have both. It cannot have just direction, or it cannot just have magnitude. It's got to have both. Now, we're going to indicate our vectors with an arrow. Okay? It may be an upper or lowercase. It doesn't matter. We're also going to indicate with the direction symbol. Okay? With the direction symbol. Now, force on a particle is a vector quantity. So we have to describe it in terms of its characteristics. Its point of application. And of course, its magnitude. And its direction. Now, I was thinking about forces this morning as I came into the building. As I was actually waiting at the door for somebody to unlock the door for me. So let's say we have a door. And this is a very small door. Okay, it's got a hinge that runs down this side. Okay, so we can assume that that door pivots on that hinge. Where do we exhibit, or where do we push on the door? Probably where it's got a door plate, right? Where is the force exerted on that door? Where is that force? You're thinking, oh, this is a trick question. Well, if I walk up to the door and I push the door, where am I exerting the force? If I push on the handle, I'm pushing on the handle. If I pull on the handle, I'm pulling on the handle, right? So I'm going to say that my force, and it's really hard to do this on a two-dimensional board, okay? What I'm saying is I'm pushing this way. Okay, does that make sense? But I'm going to draw an arrow that says I'm pushing, and that's a pretty sorry looking arrow, isn't it? I'm pushing right here. Okay? Now, in a description of that force, it's going to have magnitude, it's going to have direction, and if we characterize it further, it's going to cause really a change in the position of the door, right? You understand what I'm saying? So the door, instead of being closed, it's now going to be open. It's going to pivot on that hinge. Okay? Would the force be constant as I push on the door to open the door? Think about that question. Think about that question. Think about your doors. I mean, you don't have these fancy doors like we have at the college that you got to push the button or scan to get in the morning time. You just push your door. Does the force remain constant? No. The force changes. Okay? Now, had you left something behind the door, you would have to push harder to get it open. If the door had a magnetic lock, and once you got past the magnetic lock, it would require less force. Would the direction change? Think about you walk up to the door. You push the door straight, what does the door do? It doesn't stay, it swings. So if you continue to push on the door, what's gonna happen? Your direction is gonna change that you're adding force to because it changes. Okay, so all of those things we have to take into account when making a calculation based on forces. Now, as we look at forces, okay, we look at forces in terms of vector addition. What is vector addition? It's the sum of the magnitude and direction of all vectors applied in a system. Now, if I have a vector, if I have a point, if I have a point P, okay, this is point P, okay, really original there, point P, right? If I apply a force at point P in this direction, which we will call A, and I apply a force at point B, excuse me, in that direction, what happens to point B? Well, it depends on the magnitude and direction of those forces, right? We can rewrite the force that's exhibited on point P as something called a resultant force. And this is the sum of our applied forces. So our resultant force is the sum of force A plus force B. Okay? We have two, maybe three different ways that we can do that. The first way is referred to as the parallelogram method. And if we want to be a little bit less politically correct, it's the head to tail method. Okay, so we take vector A and we move vector B. I don't like that. Okay, so if we do it head to tail, we're gonna come up, I like purple today, how about that? With the resultant vector R. Now, if we do it with the parallelogram method, we have to add our vectors head to tail, just as we did before. Now, we can draw them in a different order. So that we've got a parallelogram. And our resultant goes from where we started to where we ended at. Okay? So we have those two methods to describe our vector addition. Now, if we're looking at this, you're probably thinking, oh, all we're going to do is draw boxes and arrays. Well, remember, a vector has magnitude and direction. So we're going to look at it in terms of magnitude and direction based on either a Cartesian coordinate system or a spatial polar coordinate system. Okay? And that's where we are going to move to towards the end of class. So if we've got this relationship for two vectors, okay, that is also equal to this relationship. It doesn't, oh, sorry, I wrote it the same way, didn't I? It doesn't matter what order we add them together. But let's say we add a third vector. Let's say we have vector A, vector B, and vector C all acting on this same point P. So that vector A plus vector B plus vector C are all equal to our resultant vector. And it doesn't matter what order we write them. Okay? And this is referred to as which property of mathematics? There's a property, A plus B plus C is equal to something, C plus B plus A is equal to something, C plus A plus B, B plus A plus C.
Cumulative.
The cumulative property of addition. Okay? So, vectors can be added just like numbers, with the understanding that you're looking at magnitude and you're looking at direction. Now, if I have a vector, let's say I have vector A. If I put it in absolute values, this indicates magnitude only. So a magnitude number. Okay? Now, can I add just magnitudes? Let's say in this particular case, one of these was 5 pounds, one of these was 7 pounds, and this other was 9 pounds. Can I add 5 plus 7 plus 9 and get the magnitude of my vector? Can I do that? What do I notice about the three vectors? Are they all in the same direction? No. So if I'm looking at the sum, which would give me the resultant has to take into account what? Magnitude and direction. So I cannot just simply plug 5 plus 7 plus 9, which is what, 21? That would not be the magnitude, because they're not all acting in the same direction. They're all acting in opposite or different directions, okay? There are 4 cases of vector addition, 4 ways we can do vector addition, okay? Case number 1. Now, bear with me. All of the tips on these things are bent, so the line doesn't come out perfectly straight. But let's say I have a vector A that's 10 pounds, a force, and a vector B, which is 12 pounds. They're acting in the same plane along the same line of action. Okay? So vector A in case 1 plus vector B for case 1 is equal to my resultant. Can I add these directly? Yes, they're working in the same direction. Okay, along the same plane. So 10 pounds plus 12 pounds is equal to my resultant vector of 22 pounds. Now, that's not a complete description, okay? Because a vector has to have magnitude and direction. So if we're gonna work on the Cartesian coordinate system, I like the Cartesian coordinate system. You know, that's the X, Y graph. We have a degrees of 0 degrees here, 90 degrees here, 180 degrees here, and 270 degrees here. For a vector to occur, it's got to have magnitude and direction. So the resultant vector would be what here? It would be, if we start here, it would be essentially a vector over the top of that, right? So we've got to include direction, so our direction is at 0 degrees because we're going this way. Now, had we added our vector, here's our point P. We still have the same vectors, okay? But now instead of to the right on the x-axis, they're to the left on the x-axis. So our R would be still 22 pounds at an angle of 180 degrees. Or R is a negative 22 pounds at an angle of 0 degrees. What does that mean? Do you understand the difference there? 180 says we're going back from 0 degrees on the XY plane. Negative 22 means we're going back in the direction of 0 degrees. So we can denote it either way. Why is that important? Why is that important? Because we don't take the vector difference, we take the vector sum. And we've got to either indicate the direction of the force in magnitude or the direction of the force in our angle. And sometimes it may be convenient to put it as negative 22 pounds. Okay, so that's our first case of vector addition. The easiest case, right? Wouldn't you say the easiest case? Okay. Case number 2. Vector A is 10 pounds. And vector B, and along the same exact plane, is 12 pounds. Okay? Now you're thinking, oh, that looks just like the first one. It's similar. The first, they were going in the same direction. And this one, they're going in opposite direction. So our resultant is still equal to the sum of vector A plus vector B. Okay? Which in our case is 10 pounds plus a minus 12 pounds. Why is it minus? Because it's in the opposite direction. So our resultant here is a negative 2 pounds. Now, since we have a force of an 82 pounds, what angle do we have? We're assuming this is along the x-axis. That angle would be 0 degrees in our description. Or, what could we put? We could put 2 pounds at 180 degrees. Moving it back to the left. Moving it back to the left. Okay. We good on those? The two simplest cases. The two simplest cases. And everybody likes to start off simple, right? Okay. Now, let's move to case number 3. In case number 3, we have a vector, and we have a vector that have a 90-degree angle. Vector A is 10 pounds. Vector B is 12 pounds. Okay? So now, R is still, by definition, vector R, the resultant vector, vector A plus vector B. Right? Nothing's changed. We're still taking a vector sum. How do we add these? We can't just draw a resultant vector. We've got to move over here. There's vector A. And then we move vector B to the end. This is vector B, so that we get a resultant vector R. So now we've got an angle for sure. It's not along the x-axis or along the y-axis. We have an angle that we have to solve for. Now, when looking at a right triangle, math becomes useful, okay? There's a theorem that most of us will use at some point in time that, they're gonna say, I did not learn this in physics, I didn't learn this in chemistry, I learned this from having to do something, okay? And that's the right triangle math, okay? Which is based on Pythagorean's theorem. Pythagorean's theorem governs right angle triangles, okay? So if I have a length of A and a length of B and I'm looking for a length of C, I can use Pythagorean's theorem. C squared is equal to A squared plus B squared. Or C is equal to the square root of A squared plus B squared, right? So I can find the length, the magnitude of my side, okay? So C would be square root of 10 squared plus 12 squared. That's 100 plus 144, so that's 244. So square root of 244, 15 squared is 225, right? A little bit better than 15. Y'all got a calculator, you can push the buttons, right? No? Possibly square root of that, around 15 and a half, somewhere in that neighborhood. 15.62. So our magnitude is 15.62 pounds. Our magnitude is 15.62 pounds. Now, along with that, we've got to find the angle here that force is bending through. Now, you can go back and use something called SOHCAHTOA. Remember that? I had to go back and look up some of those. But SOHCAHTOA, it's after some infamous Indian tribe, right? The SOHCAHTOA Indian tribe. Okay. Well, if we use tangent, Changing of our angle is equal to opposite over adjacent. We have the opposite and we have the adjacent. So we can plug that in. That's equal to opposite, which was 12, right? Over 10. So theta is equal to the inverse tangent of 12 over 10, which gives us an angle, I did the math on this earlier, of 50.2 degrees. So this angle here is 50.2 degrees. So our resultant force is equal to 15.62 pounds at an angle of 50.2 degrees. At an angle of 50.2 degrees. Okay. Questions on the first three cases? Now we're going to hold over case 4 to Wednesday because it's going to take a lot longer to talk about it. So turn me off there.
Yeah.